So grand a theory as the theory of LSH families wouldn't be nearly so grand if there were only one example, the min-hash functions, that we could use to start. But in fact, there are many interesting base families to start with, and the same and or constructions can be used with any of them. Here we are going to introduce first the random hyperplane LSH family, which is appropriate when the distance measure is cosine distance, and then we'll see an LSH family for the conventional Euclidean distance. Recall that the cosine distance between two vectors is the angle between them. As we are measuring angles in degrees, the value of a cosine distance is a number between 0 and 180, not between 0 and 1 as it was for Jacquard distance, or a number between 0 and infinity as it is for many other distance measures such as Euclidean. We're going to learn about an LSH family of hash functions that works for cosine distance, in particular for any distances d1 and d2, with d1 less than d2. We can view this family as d1, d2, 1 minus d1 over 180, 1 minus d2 over 180 sensitive. This is exactly the way we view the min-hash functions except for the scaling factor of 180 because of our decision to measure angles in units of degrees. The LSH family is called random hyperplanes. Here's how we construct the random hyperplane hash functions. Each of these functions is defined by some vector v. Call the hash function associated with vector v h sub v. And I should warn you that our notion of a vector is a little non-standard. We are really picking a direction for a vector, but not a scale factor. That is, if you double the components of a vector v, we regard that as the same vector. And in fact, if you reverse the vector by, say, multiplying its components by -1, you again have the same vector. The value of h of v applied to vector x is either +1 or -1. It is +1 if the dot product of v and x is positive, and it is -1 if this dot product is negative. Notice I'm not saying what happens if v and x are perpendicular, that is, the dot product is exactly 0. In a vector space with real value dimensions, the probability of this happening is essentially 0, but to be precise, we should state something to do when the dot product is 0. Say put x in the +1 bucket. The LSH family is all the functions h sub v. Remember that really h sub v is a function that takes two vectors x and y and says yes or no. In this sense, h of v says yes if and only if x and y are in the same bucket, that is, the dot products of x and y with v have the same sign. Notice that we're really okay thinking of all multiples of a vector v as the same vector, even if that multiple is a negative number like -1, because all multiples of v give the same yes or no answers about a pair of vectors x and y. Analogous to the theorem about min-hash functions and Jacquard distance, we have the following theorem. For any of the random hyperplane hash functions, the probability that h of x equals h of y is 1 minus 1/180th of the angle between x and y. This picture explains why we can get cosine distance from the random hyperplane hash functions. First, let us look at the plane containing the two vectors x and y, whose cosine distance we want to determine. Any vector v has a hyperplane normal to v, that is, the set of all points whose dot product with p is 0. This hyperplane is what we are really choosing when we choose v, which is why the method got its name random hyperplanes. The dashed line is the intersection of this hyperplane with the plane of x and y. The vector we show as v is really the projection of v into the plane of x and y. The particular random hyperplane we chose has the property that its intersection separates x and y. That is, x is in the same direction as v relative to the dashed line, while y is in the opposite direction. Thus, the dot product of x with v will be positive, and the dot product of y with v will be negative. Now here's what it looks like when the random hyperplane is such that both x and y are on the same side of the hyperplane. The one shown is a blue dashed line. Note that what is important here is not that the blue vector v is between x and y. That's a coincidence. What is important is that x and y are on the same side of the dashed blue line, and as a result, the dot product of both x and y with v have the same sign. As shown, that sign is positive, but if we replaced v by minus v, say like this, then the blue vector would be reversed, and the dashed blue line would be the same. Both dot products of x and y with v would be negative, but what is important is that they would still have the same sign. So suppose theta is the angle between x and y. The hyperplane makes some angle with x and y. We can think of all the possible angles of this hyperplane starting out with the direction that coincides with y. It can then sweep out 180 degrees, sort of like this. Okay, until we come to the continuation of y. Now, what is the probability that the situation will look like the red rather than the blue? It's theta divided by 180. Okay. That is, the red case is when h says no, so the probability of saying yes, which is any hyperplane in this area, is 1 minus theta divided by 180. Here's how we use random hyperplanes to find similar vectors in our data set, where similarity now means low cosine distance. First, we pick a number of vectors at random. This selection corresponds to picking some random permutations to serve as min-hash functions. But here, instead of min-hashing, we compute the dot product of each vector in our data set with each randomly chosen vector to get a sequence of +1s and -1s called a sketch. The sketch is analogous to the min-hash signature, and we can apply LSH to our sketches by thinking of them as a matrix, dividing the matrix into bands and proceeding as we did for min-hash signatures. However, with the theory of LSH families available, we have options. We can start with the LSH family of hash functions defined by each possible random hyperplane, and then apply the and or constructions in whatever order we desire. While we shall not go into this reasoning, it turns out that you can avoid having to pick random vectors v from the space of all possible vectors of some dimension d. It is sufficient to let each component of each vector be either +1 or -1. That makes the calculation of dot products easier, since there is no multiplication involved, just sums and differences of the components of the vectors to which hashing by random hyperplanes is applied. Now, let's switch our attention to an LSH family for the normal Euclidean distance. We'll pick lines in however many dimensions our space has. Each possible hash function in the LSH family corresponds to a line. The line will be partitioned into segments of some length a. Each segment corresponds to a bucket. Each point x in the d-dimensional Euclidean space is hashed by projecting it onto the line for this hash function. That is, find the hyperplane perpendicular to the line that goes through the point x and see where on the line the hyperplane intersects the line. That is the projection of the point x onto the line. The reason this works as an LSH family of hash functions is that points that are close to the space must always project onto points that are close on the line. Thus, they have a good chance of falling into the same bucket, although by bad luck, their projections might be separated by a bucket boundary. On the other hand, if points are far apart, they might fall into the same bucket if the line between them was almost perpendicular to the line that defines the hash function, but most likely they will be in different buckets. So here's a picture of what is going on. We're going to look at only the two-dimensional space for simplicity, but similar ideas will work in any number of dimensions. We see a randomly chosen line divided into buckets of width a. That's this, of course. And here are 2 points at distance d, here and here. When we project them onto the chosen line, the distance between them is d cosine theta, where theta is the angle the chosen line makes with the line between the 2 points. Notice that if d cosine theta is bigger than a, there is no chance that the 2 points fall in the same bucket. If d is very much greater than a, theta must be almost 90 degrees for the points to land in the same bucket. On the other hand, if d is much smaller than a, there is a good chance that the 2 points land in the same bucket. Since d cosine theta is surely no bigger than d, the probability that no bucket boundary separates the projections of the 2 points is at least 1 minus d over a. So if 2 points have Euclidean distance at least 2a, then there is zero chance they fall into the same bucket unless theta is in the range of 60 to 90 degrees. Since theta is random in the range 0 to 90, there is at most 1/3 probability of sharing a bucket, and thus at most 1/3 chance that a randomly chosen hash function from the LSH family will say yes. On the other hand, if points are at distance at most a over 2, then they share a bucket with at least 50% probability. That is, the probability of a yes answer for these 2 points is at least a half. We can combine these two observations to say that for any value of a, we can have an a over 2, 2a, a half, a third sensitive family of hash functions for Euclidean distance in 2 dimensions. However, there is something unsatisfying about that analysis. For min-hashing or random hyperplanes, we were able to start with a DEPQ sensitive family for any d and e as long as d was less than e. And we could then drive p to 1 and q to 0 using the and or constructions. Here we don't seem to be able to get d and e to be as close as we want. We seem to need d to be at least 4 times e. But we were being overly pessimistic. In fact, as long as d is less than e, we know that the probability that points at distance d have a better chance of falling into the same buckets than do points at a larger distance e. As a consequence, we know that for any d and e with d less than e, the hash functions based on lines and bucket size a is a DEPQ sensitive family for Euclidean distance for some probabilities p and q, such that p is greater than q. Starting with this family, we can amplify the probabilities to make p as close to 1 as we like and q as close to 0 as we like, while still allowing d and e to be as close as we like, as long as e is strictly larger than d.